Okay, so we've covered a couple different systems so far. So strong, strong, and then we just did weak acid being titrated with a strong base, and now we'll sort of flip that with weak base titrated with strong acid. This turns out to be identical in terms of process, but only different in that we're dealing with a KB instead of a Ka. So the example here is that we have a sample of 40 mils of NH3 ammonia, and the titrant is the strong acid HCl. So just like before, I like to start by figuring out where the equivalence volume is. Again, that's the equimolar point where we have exactly the same number of moles of acid being added to the base because we know they react 1 to 1. And so you can set that up dimensionally, or you can do just a simple M1V1 where we have volume at 40 mils of 0.1 molar NH3, and then that's equal to some X. That's our equivalence volume at 0.1 molar of HCl. That gives us 40 mils. So that gives us a sort of reference point that we know that everything less than 40 mils addition is going to be in the pre-equivalence region or the buffer region. Everything post 40 mils is going to be in the post-equivalence region. Okay, so then the next logical step is just to figure out what the pH is before you've added any acid titrant. So that's the 0 mil condition. And we're talking about a weak base in water. That's what we have. So we're just thinking about that weak base association. Here's the reaction, make an ice table, all the same as we've done before. So we pop that in for Kb, we solve for X, via an approximation we get something like this. You can check that that works out, and the approximation is valid, and that is equal to X, and we know X here is equal to hydroxide ion concentration. So we need to use Kw to convert that to H plus before we can make take the negative log of figure out pH. Do that and you get a value of 11.13 for the initial pH, which makes sense because now we're talking about a weak base in water, so our titration curve is going to flip, at least with respect to that y-axis. So we're starting at a high pH, we're adding strong acid until we get to a low pH. So that's our initial point. So next point is anywhere in the pre-equivalence region. We already figured out that equivalence point's at 40 mils, so really anything between 0 and 40. What are we doing in that range? Well, we're taking a weak base and we're adding some amount of strong acid, or H plus or H3O plus, which is going to produce the conjugate acid and hydroxide. So we can just tabulate everything just like we did in the weak acid being titrated with a strong base, and take stock of what we have after the reaction occurs. So tabulated, it should look something like this. So if you remember from the previous video, I like to take the initial concentration and then multiply by its volume. That would give me moles in principle, and then divide again by the new volume because we had the old volume 40 mils plus 20 that we added. That'll give me the concentration of NH3 before we've allowed these things to react. Same is true for the H plus or the H3O. Starting out with 0.1 molar HCl, 20 mils of it, that gives you the moles, divided by the total volume, which is 60 in this case. So I've tabulated those things here as 0.0667 and 0.033. We know these things are going to react to completion because this is a neutralization reaction with a very large K. So that depletes all of this and then subtracts the same quantity from NH3. And in doing so, it converts that 0.033 of the weak base into 0.033 of the conjugate acid, and we're left with this condition. So we can set these up in an equilibrium expression equal to Kb and solve. Or we could recognize that this is a buffer region, just like we had before. Anytime we're pre-equivalence with a weak base or acid and its corresponding conjugate, and we notice that we have both of these things present, so we could just simplify this and do the Henderson-Hasselbalch equation, or we could just write out the Kb expression and solve for that. Both will give you the right answer. And so the Henderson-Hasselbalch equation is here. Pop in 4.74, which is the which I just realized that's the pKb, because that's negative log of the Kb, so I need to actually convert this to a pKa, which I did here, so 14 minus the pKb, that gives me a value of 9.255 here, plus log of the ratio of the two species, which in this unique situation, because we added exactly half of the equivalence, 20 mils, that term is 1, log 1 is 0, and so the pH is equal to 9.255. So at the equivalence point, we already determined that was at 40 mils. Remember, what that means is we've added exactly enough acid to completely convert all of the base to its conjugate. So in other words, all of the original NH3, all those moles, are now moles of NH4 plus. And so what do we have in the system at that moment? Well, we just have NH4 plus and water. And so NH4 plus is going to react with water as a weak acid, which is going to shift the pH to below 7 instead of above 7, which is what we had when we had a weak acid plus a strong base. So that means we can write up an equilibrium expression of NH4 plus water. We can allow that to relax to equilibrium and then use that to determine what the pH of the system at equilibrium is. So the important thing is to remember that for our initial condition of the NH4+, it's the same as our initial amount of NH3, because at equivalence, we've converted all of that NH3 into NH4, but we've also doubled our volume. And so to figure out how many moles of NH3, that would just be 0.1 times its 40. That gives me the moles. But now I need to divide again by the total volume, which is going to be 40, the initial volume, plus the 40 we added to reach equivalence. And so we're going to be at exactly half of the concentration that we were originally starting with. And now we can allow this thing to change and relax to equilibrium and compute what that pH is going to be. So I can fill out the rest of my ice table just like always. So that I can then plug into the expression for Kb. So I have Kb is equal to x squared over 0.05 minus x. Make an approximation, and that gives me 1.5 times 10 to the minus 6 for x. You should confirm that offline. And since this x is the H3O plus here, just simply taking the negative log of that gives us our pH, and the pH in this case is 5.82. Okay, so the post-equivalence region is the last bit, so example is 60 mils, just like we've done in the past. So you're just taking the weak base and you're adding excess acid here. So write out the expression like this. I wrote it out just in terms of H plus instead of H3O plus, just to give you the other perspective. They're identical. You can write them either way. And remember, so you're starting with whatever the initial concentration of ammonia is when you've added the 60 mils. And so that's 0.1 times the 40 of the initial divided by the total volume. And similarly, H plus, we have 0.1 molar. We're adding 60 mils of it. That gives moles of H plus that are added over the total volume. And we have no NH4 plus to start with. Tabulate those really quickly, you can see that you have an excess of H plus, and so that means it's going to destroy all of the NH3 minus 0.04 of it, and we're going to have some excess 0.02 left of the H plus. And for every mole of NH3 that we destroy, we create one equivalent of the NH4, which is why you get the plus 0.04. So we can take this, and just like we talked about in the previous example of this, the sort of flip version of the weak acid being titrated with a strong base, this itself could go and proceed to react, because it's a weak acid, with water, and that could make H3O plus and NH3, which this is an acid, so that could make the system acidic, but it's going to be really negligible because the Ka here is really small, and so we don't really need to consider that, and all we need to consider is this. So this is equal to the concentration of protons, so simply taking the negative log of that value will give us what we need. And in that case, that equals a pH of 12.3. So for the titration of a weak base with a strong acid, we just get the inverse of what we had for the titration of a weak acid with a strong base. We start at higher pHs because that's the weak base in pure water. So we had 11.2. Figured out that equimolar amounts of the acid and base would take 40 milliliters. That's our equivalence volume at 5.28 pH. And we, just like we before, anytime we were sub-equivalence or pre-equivalence in this region, this whole region we considered the buffer zone, where we had both, in this case, NH3 and NH4 present, which we could use the Henderson-Hasselbalch to solve this region. And then anything post-equivalence, we just had excess protons. And we talked about, in both of these examples, this sort of unique point here, which is really nice, where pH is equal to pKa, and that's when both of these things are equal. So you have the Henderson-Hasselbalch equation, which is pH equal to pKa plus log the base over the acid. When those two terms are 1, this thing becomes 0, and pH is equal to pKa. And so that's always going to be the center point, which is halfway to the equivalence point. And so that's a nice thing to sort of keep in the back of your mind and make sure all of this sort of works out. So when you make a plot like this, if you make any mistakes, it should be pretty obvious to you, as long as not every single point is a mistake. If something lies very far off of the line that you're expecting, then you probably made a mistake. And so there's a lot of intuitive aspects of this work too.